here's again this pathway that leads to pyruvate from these different amino acids. We did pyridoxal phosphate. The last reactions we want to do involve both pyridoxal phosphate and tetrahydrofolate. And so we did alanine. So alanine, remember this one reaction, alanine aminotransferase transamination reaction. Alanines convert to pyruvate and alpha-ketoglutarate to glutamate. So that's a pyridoxal phosphate reaction. So first one we need serine. Serine dehydratase, another PLP-dependent enzyme. Serine goes to pyruvate and water and ammonia. And so the last one I want to do has to do with glycine. Glycine's a little more complicated. And so glycine is here. And so that's what I want to start with. So for glycine, we're sort of doing this in the context of amino acids can be degraded to pyruvate. So let's start with that. So let's remember what glycine looks like. So we want to convert glycine to pyruvate. And so you see the problem. Glycine has 2 carbons and pyruvate has 3 carbons. So we need one more carbon atom. Right? So that's why it gets a little more complicated. That's why glycine can go in this direction via the glycine cleavage enzyme, and it can go in this direction with serine via serine hydroxymethyltransferase. So both of these enzymes involve pyridoxal phosphate. It's shown here for serine hydroxymethyltransferase, not as the glycine cleavage, but it is. And both of these enzymes use tetrahydrofolate as a substrate or product, and they both produce this thing, N5-methylene tetrahydrofolate. So that's what I want to try to go through in various levels of detail. Let me just sort of sketch out sort of what's going on here first, and then go into more detail. So if you're going to make pyruvate from glycine, what you have to do is take 2 molecules of glycine. And we're going to take one of the carbon atoms from one of the glycines and add it to the other one. And then we're going to be able to make pyruvate. So what's going to happen is that this glycine cleavage enzyme which I'm not going to discuss in any detail, but as you may be able to see on the slide, the products of this enzyme are basically takes glycine and just breaks it apart into its 3 components. The amino group of the glycine is released as ammonium ion. The carboxylate group is released as CO2. And this is actually a pyridoxal phosphate-dependent decarboxylation reaction. So this enzyme is PLP. It forms a shift base to using the amino group of glycine, and then it decarboxylates, and the pyridoxal phosphate stabilizes the carbanion formed that way. All right, so that's these 2 components. And then what about this? That's the carbon that's going to be added to the second glycine to make the serine. So that carbon is released in the form of what I'll draw this way, which you can call methylene tetrahydrofolate. Right, and you call it N5-N10 methylene tetrahydrofolate if you want to. All right, so this is a product of the glycine cleavage enzyme. And that product is a substrate of this enzyme, serine hydroxymethyltransferase. So serine hydroxymethyltransferase is going to take the second glycine, and it's going to combine it with this to produce serine. Right, so the reaction is glycine plus THF plus, I believe, water, because we need an oxygen. And that gives us serine. Right? So that's how we take 4 carbons from glycine. We take add 1 carbon to this, that gives us 3 serine, and the 4th carbon will lose the CO2. Right? And then once we have serine, we saw last week that serine dehydratase can convert this to pyruvate plus ammonia. So the glycine cleavage system is actually a little bit more complicated reaction than one might think. It's actually an oxidation reaction, so it involves NAD. It actually has lipoamide as a coenzyme, and I'm not going to go through the mechanism of that enzyme. But I do want to go through the mechanism of serine hydroxymethyltransferase.
Question.
Okay, so serine hydroxymethyltransferase I'm going to do it not, I said the issue is to make pyruvate. Let me actually run the reaction in the reverse direction to make glycine from serine for some reason, which is actually an important reaction metabolically. So the reaction is going to be, it's the reverse of what I just wrote up there. I won't write it again. But we're going to take serine and we're going to remove this group and give it to the tetrahydrofolate. So the products are going to be glycine, water from the side chain, and again, this methylene tetrahydrofolate. All right, so the first question I want to address is what is tetrahydrofolate? So tetrahydrofolate is a important molecule in metabolism. And like a lot of these molecules, it has a rather complex structure, most of which we don't have to know, fortunately. And so this is what it looks like. So that's, it has glutamic acid off to the side. And I think I drew it correctly. I think I slide. So here it is. Oh, I left out the para-aminobenzoate part. So let's just call this R.
It's not linked to glutamic acid?
Yeah, so glutamic acid is at the far right, and then there's a para-aminobenzoate. But this is actually even more than the important part. The important part is actually this nitrogen, which in the numbering system, they've numbered the atoms for you. This ends up being atom number 5, so that's N5, and this nitrogen, which is N10. All right, so on the previous slides, the product was N5N10 methylene. That's because the group is going to be attached to these two nitrogens. And so that's really all that I want you to know about Bchm. It's just those two nitrogens, and then they're linked by those carbon atoms. So these nitrogens can act as nucleophiles, and so one reaction that you might imagine, although I'm not sure it's a metabolically important reaction, but for example, if this were to be mixed with an aldehyde, let's just say formaldehyde, one or the other of these nitrogens can attack the formaldehyde as a nucleophile, and we could get an adduct that would look like this. So this is the kind of thing that forms when an amine attacks a carbonyl group, and it's on the way to forming a shift base. And so that's, I chose nitrogen number 10 kind of arbitrarily. But there's also this nitrogen number 5. Nitrogen number 5 then can get in the act, and displace water. And that is how, at least in a chemical sense, that's how you could form this N5N10 methylene THF. Right, CH2, remember, is a methylene group. So an N5N10 methylene THF, the methylene group is joined to nitrogen number 5 and to nitrogen number 10. So that's what THF does. The function of THF in metabolism is to sort of carry single carbons or single carbon units. In this case, it's a methylene group. And so that carbon is going to come from some donor molecule, and then it's going to be given up to some acceptor molecule in some other enzymatic reaction. So let me go through now the actual mechanism. This is another one of these multi-step mechanisms with a lot of arrow pushing. So for serine hydroxymethyltransferase, it's a pyridoxal phosphate dependent enzyme. It has pyridoxal phosphate linked to a lysine in the form of a Schiff base. So I'm not going to draw all that structure again because we saw it last week. But we'll start with the enzyme covalently bonded to PLP. This will react with the amino group of serine. Again, I'm going in the serine to glycine direction. And we'll get the Schiff base of pyridoxal phosphate with the serine. And so remember this from last week. So there's the same old Schiff base, and we've seen this one several times already. And in this case, remember serine dehydratase. My next slide reminds you of that. Remember that in serine dehydratase, there's a schematic I found in the book. We're going to remove the alpha hydrogen, or the hydrogen from the alpha carbon, and that makes a carbanion. And we're going to do that here also for serine hydroxymethyltransferase. So a base on the enzyme, probably that lysine, but a base. Again, we're going to get a resonance stabilized carbanion. Again, we can delocalize that. It's the same carbanions from serine dehydratase. And again, in serine dehydratase, the next step was to eliminate the side chain as water. And that's shown in this figure is all going in one step, and maybe it does. Well, let's do that. This has to pick up a proton, and that's going to give us the same intermediate form last week. So now in serine dehydratase, you remember that the lysine reacted with the Schiff base and displaced this thing. That was the amino acrylate product, and then that spontaneously underwent tautomerization and hydrolysis. And in this case, that's not what's going to happen. In this case, now we've got a CH2 group, and that CH2 group is going to be transferred to the tetrahydrofolate. So the enzyme will bind tetrahydrofolate, and So now this same reaction that I sketched out and then erased, here it is almost completely erased. We have an aldehyde, here we have an electrophile, and what's going to happen? The tetrahydrofolate is going to attack, and I don't know which N attacks first, so I don't know if it really matters. Let's say number 5 attacks. So the nucleophile attacking this electrophile will protonate the carbon, and that will give us an intermediate. Where the CH2 is covalently bonded to N5. Here's the N10 sitting right there.
What is that nitrogen attached to when it's attacking the CH2?
So it's attached to this whole ring.
Okay.
Yeah, this is the THF. And it's too big to draw it and put all the atoms in. Yes.
Would it still be in the ring form that we have it?
The THF is always in the ring form, except these are not unless there's a carbon bridging them. Okay, but otherwise, the THF, all the other bits of it are unchanged.
This isn't
Yeah, so here's the THF again. It's this nitrogen, which is, this whole structure doesn't change. So that nitrogen number 5 is going to attack. Yeah. All right, so to finish the transfer, now nitrogen number 10 has to attack. And it's the same nucleophilic attack on that carbon. Carbon's perhaps not so nucleophilic anymore, but will displace the amino acid, pick up another proton from presumably some other acid in the active site. And this is going to give us what? This is going to give us, here's the THF. Okay, so again, this is the N5, N10 methylene tetrahydrofolate product. So that's a product that fuses away from the enzyme. And what's left? So up here, let's see, we displaced the carbon. The carbon is now over there on the THF. And we're left with the shift base of glycine to the pyridoxal phosphate. Okay. So we took off the proton from the serine up here to be able to eliminate water. Right? And then we put a proton back on when the N5 attacked, or when the first nitrogen attacked. And then we put the second proton on when the second nitrogen attacked and grabbed the CH2. Okay. So that's how this enzyme works. The glycine has to be displaced by the lysine. Remember the lysine side chain amino group will react with this shift base and displace glycine. Right, and that's the same final step as in serine dehydratase. And so here's serine dehydratase. Here's the other part of the figure in the book, which shows the serine hydroxymethyl-transferase reaction. This is perhaps a little bit abbreviated reaction. Doesn't show maybe all the steps that I showed. I think it shows the mechanism. Note that there's glycine going to serine. So they're showing you in this group, in the glycine to serine direction, starting with the shift base of glycine bound to PLP. Right. I did it in the reverse direction. I did it starting with serine, makes the shift base to the pyridoxal phosphate, and then you get glycine. And so they left out the details of the tetrahydrofolate, which I showed. Any questions? Yes.
Aside from, so would you, or is it normal to find serine being converted into glycine?
So that's leads into my next point, actually. I started this saying we're trying to make pyruvate, and this is sort of going in the wrong direction. And so this direction, glycine to serine, again, serine could be converted to pyruvate. In fact, the reaction does go in this direction as well, in biologic terms. And so I think that's the next point I wanted to address. Let me get to that in a minute. So we started with serine, and we removed the side chain carbon, and now we have the methylene tetrahydrofolate. Okay, so now this carbon atom is stuck to THF, and now it's available for other metabolic processes. And so that's one point, and I'll elaborate on that a little bit in a minute. The other thing is that there's a set of enzymes in the cell that can use methylene THF as a substrate. And one such enzyme is an enzyme that's a reductase, which can reduce this methylene group to a methyl group. And reducing agent is NADH. And I believe it makes N5 methyl. Right, everything else is the same. Right, but that's now the methylene group is now a methyl group. Right? And so that might be useful in metabolism. So here's the reaction I did. We took the side chain of serine and we made the methylene THF. We also remember the glycine cleavage enzyme does the same thing. It takes the CH2 group and glycine and puts it there as well, makes methylene THF. All right, and then this reductase makes N5 methyl THF. And then there's another enzyme that will oxidize this. And so the oxidizing agent turns out to be NADP, make NADPH. In the oxidized form, can have, I believe, this structure. And the rest of the cofactors unchanged. And so now the carbon is at a more oxidized oxidation state. So the methylene carbon is at the oxidation state of an aldehyde because it has 2 bonds to nitrogen, just like an aldehyde has 2 bonds to oxygen. I'm considering oxygen and nitrogen essentially the same from the oxidation standpoint. This is at the oxidation state of say, methanol, where it's got 1 bond to a heteroatom, N instead of O. This is at the oxidation state of formic acid. It has 3 bonds to nitrogens. So, so that's another product you can get from this. So that's down here. And they're showing it as a protonated form with some delocalization of electrons. So where would the proton go? Oh, yeah, I guess if you protonated it here, that would give you a delocalize. But anyway, there's the this is called methenyl THF. And this the figure in the book is a little more elaborate. I don't know if I can complete the figure. Here's a complete figure. So here's methyl THF, here's methylene, here's this methenyl, and then these are other forms that can be made just by hydrolyzing this or this. And, you know, that's why I didn't show this on the previous slide. So you have to know these, but these are all equivalent forms, and these all have the carbon in the most oxidized form of the three. So if the methyl is the most reduced, the CH2 is oxidized relative to methyl by 2 electrons, then another 2 electron oxidation would be this form, and which is an oxidation sensitive. Okay, so the point is that once you've made this methylene THF, once you've taken, say, the carbon from serine, now it can be converted to all three of these forms, and they're all used in metabolism in various ways. So I'm not going to go into any of the details, but let me just show you the reactions that I believe occur in humans, and maybe others in humans. But one way that this methyl THF is used is that methyl group is the source of the methyl group in the side chain of methionine. Right, so you all remember the side chain methionine, 2 CH2s, and a sulfur, and a methyl group. So that methyl group comes from methylene THF. This methylene THF, that carbon atom can become the methyl group of thymine or thymidine. So, if you don't know thymidine, thymidine looks like this. Thymidine. And it has a methyl group, and that carbon atom comes from this molecule. Right? So if the cell needs to make thymidine, it can use serine hydroxymethyltransferase to generate methylene THF, and then use that as a source of the methyl group for the thymidine. The methenyl carbon is used to construct adenine and guanine. And if you look in, I don't remember what chapter of the book it is, I looked at it today. It's kind of a lengthy pathway to make these two things. And I think 2 of the carbons come from this carbon. Right? So again, that carbon could originate, say, serine. And so why do you need thymidine monophosphate, and why do you need adenine and guanine? Those, of course, are components of DNA. So if you want to make DNA, that's how you do it. So turns out that this reaction is important for this further metabolism. This reaction is very important in cancer cells, it turns out. And this reaction and the glycine cleavage reaction, because both of those are ways to make this. And you know, cancer cells grow rapidly, and they're constantly replicating DNA and dividing, so they need to make DNA at much higher levels than other tissues, other non-dividing cells, right? So they need to make thymidine monophosphate and adenine and guanine, and to do that they need this carbon. So they're doing this reaction at much higher levels than ordinary cells. So that's the significance of this in metabolism. Maybe that's all I want to say. Any questions? Yes.
Is there any particular reason why you like the reducing agent and the oxidizing agent, like they're using?
Yeah, that's a good. I don't know. Yeah, this is what's shown in the book, and I hope it's right. This reaction is reversible, so it's not really necessarily you're making any DPH necessarily. Any other questions? Yes.
So would the amount of folate in one's diet affect their cancer risk at all?
Does the amount of folate in the diet affect cancer risk?
For other reasons.
It's probably, you need it for other reasons, so it's probably. Any other questions? Yes.
Just to clarify that one, so you're saying that in cancer cells you find these reactions occurring more?
Yeah, so glycine metabolism, which is related to this, is people are finding that it's important. I guess maybe the enzyme level will increase.
Right.
Why is that? Well, it's thought to be because of these kinds of reactions. This reaction and the glycine cleavage. Presumably, people are think of that as like a drug target, not to inhibit this enzyme. Good. Might have other secondary effects. So I want to spend the rest of this time today, and maybe some next Wednesday, doing another aspect of amino acid metabolism, which is a little bit different than we've been talking about, and that is the urea cycle. The urea cycle is a way to get rid of excess nitrogen by forming urea.
I'd be lucky, yeah.
So we saw that you can take amino acids and extract the carbon atoms. The only examples we saw were pyruvate. So alanine can be converted to pyruvate, and the amino group is transferred from alpha to alpha-ketoglutarate to make glutamate. So there's the amino group of the alanine, but of course the pyruvate can be used, for example, to make acetyl-CoA, and then either fat or anthropocyclic acid cycle. So you get in. But the point is that the glutamate now has that nitrogen atom. We saw that serine by serine dehydratase, and also glycine by glycine cleavage enzyme, we saw that serine goes to pyruvate plus water plus ammonia. And so that's the other way that amino acids can lose nitrogen. And so we need to also be able to get rid of this excess nitrogen that's produced in the form of ammonia. So we do that by making urea. So here, this is the urea cycle. The urea cycle, this is a big book that shows sort of two phases, you might say. So the upper part up here is kind of collecting amino groups. And the amino groups are collected in the form of glutamate, but also it turns out glutamine and alanine. So I'll say a little bit about that collection of amino groups. The idea is to collect amino groups from other tissues. These molecules then circulate through the blood till they reach the liver. So this is a liver cell. I guess that's the mitochondrial matrix of the liver cell. But it's in the liver cell that these amino groups are collected, and they're used to make urea. So here's urea, right? And then that's excreted in our urine. All right, so there are 20 amino acids. I already said this, glutamate and ammonia. There are 20 amino acids. If you look at their structures or remember their structures, there are 29 nitrogen atoms in these 20 amino acids. So that's a lot of nitrogens. And if you go through the textbook and look at the appropriate metabolic pathways, you'll find that of the alpha amino groups, it turns out that 10 of the alpha amino groups are transferred to alpha-ketoglutarate to make glutamate. That is, there are 10 amino transferase enzymes that are specific for different amino acids, and they all take the amino group and they give it to alpha-ketoglutarate and make glutamate. So that's 10 of the amino acids. It turns out that there's the other 10, the amino group is released as ammonium ion. Right, so that counts for all the alpha nitrogens, alpha amino groups, and 20 of the 29 carbons. And then if you look more carefully, it's kind of interesting. 5 of the side chain nitrogens end up as ammonia. I couldn't tell you which one, so maybe I could tell you 1 and 2. And then the other 4 are released as other things. 2 of them are urea. Actually, 1 of them I know is arginine. I'm not sure where the other urea comes from. Another is an amino acid called ornithine, which is involved in the urea cycle. And then another side chain nitrogen is actually released attached to THF. And again, I'm not sure which one that is, but you can probably find it. Right, so these are all the ways that nitrogens are removed from amino acids. And again, if we want to dispose of them, we want to get as many as we can to urea. Right? So the ammonium ions and the glutamate nitrogens are going to end up in urea. I'm not sure about the form of amino THF. Okay. So So the end of this whole thing is, it ends up in the liver, and it ends with the synthesis of this molecule, which is urea. Which is made by the urea cycle. So I'm going to go through the steps of the urea cycle, and what you'll see is that this is constructed from the following three molecules. The carbon atom comes from bicarbonate. One of the nitrogens comes from ammonium ion, which is produced in the liver cell from either glutamate or glutamine or alanine, I guess. And the other one actually comes from aspartate. So far we have amino groups in the form of glutamate. And we have amino groups in the form of ammonium ion that have been produced by other tissues. Right, so we have to get those groups to the liver, and then we have to regenerate ammonium ion in the liver, and we have to make aspartate. Okay. So glutamate is carried in the bloodstream. It circulates through the blood, so that's not really an issue. Ammonia, as I said last time, I think is toxic. And if it builds up to too high levels, it's toxic apparently due to osmotic issues. So rather than having free ammonium ion circulating in the cells, instead there's an enzyme called glutamine synthetase, which is going to make glutamine from the ammonia. So glutamine synthetase is going to take this glutamic acid, which I've already drawn very conveniently, and it's going to attach the ammonium ion to that carboxylate group, and it's going to make glutamine. And then the glutamine, again, it's going to circulate in the bloodstream. So glutamine actually carries two amino groups that can be disposed of. All right, so what this enzyme does, and this is the reaction, most of it catalyzed by this enzyme, it takes a carboxylate group and it joins it to an amino group and makes an amide. Right? Now, we're taking this resin stabilized carboxylate at pH 7. We're taking this protonated amino group. We're trying to make an amide, and thermodynamically, this is not a very easy reaction. So I don't know what the free energy change, it probably has in my notes. But the free energy change for this reaction, as I've written it, is very positive. So we need a source of free energy, and so the source of free energy, of course, will be ATP. So the enzyme actually first catalyzes activation of the carboxylate group using ATP in a reaction that's similar to what we've seen in other instances. And so the first thing it does is phosphorylate the carboxylate group. Using ATP as the phosphorylate group donor. So this is obviously a mixed anhydride, carboxylate with phosphoric acid. And now the enzyme is going to catalyze nucleophilic attack by the amino group that's got to pull off 2 protons, but pull off 1 proton at this point anyway. And it's going to catalyze nucleophilic attack by ammonia on this intermediate, and that will give an intermediate of this sort, which can use phosphate, and they'll have to lose a proton as well, because I left the 3rd proton there, but it will lose phosphate, it will lose the 2nd proton of the 4 that were here. Protonate. But it's a nucleophilic attack and nucleophilic displacement, and that will give us the amide. So that's glutamine synthetase. So all these 14 amino groups, 15 amino groups that are released as ammonium ion, those are quickly attached to glutamate to make glutamine, and it's the glutamine that actually circulates in the bloodstream. So if we go back to this slide, I already mentioned glutamate. So here's the things carrying the amino groups up here. So glutamate is carrying an amino group. Now glutamine, oops, I'll get to alanine in a second. Oops, I'll get to it now. Here's glutamine over here. Alanine. Alanine is carrying amino groups. It's carrying it from muscle cells. So in a muscle cell, in a muscle cell, the muscle might, might want to make pyruvate from alanine so that it can then oxidize the pyruvate and generate energy. And of course, that means using up an alpha-ketoglutarate. And there are other amino acids that a muscle cell can use, and I'm not going to go into the details. I'm not sure I know the pathways, but some of these other ones are things like valine and isoleucine, I think. Yeah, valine and isoleucine. There's a transamination reaction involving valine that also transfers the amino group to glutamate, makes some other product. You could draw the structure probably, I don't know what it's called. And the same thing for isoleucine. And then further oxidation occurs and energy is produced. And the same thing from the isoleucine, right? So, that's going to mean oxidation of the carbon atoms in these amino acids, and that's how a muscle cell can generate ATP. It's one of the ways, right? But there's a problem with this from the standpoint of a muscle, which needs to be able to generate energy very rapidly, is that each one of these reactions uses up alpha-ketoglutarate, which the muscle cell needs to be able to do the citric acid cycle. And so it's presumably for that reason that rather than making all this glutamate and secreting the glutamate to the bloodstream, which carries away alpha-ketoglutarate, the muscle then uses some of its pyruvate and takes the amino groups back and puts them on alanine. So I suppose maybe you could have kind of ignored this reaction, but certainly these reactions, actually these are more important for a muscle to generate energy. And so it's actually the alanine that is secreted. And this is the enzyme alanine aminotransferase that I talked about last week. And so this is then, the alanine is then secreted. And this is how alanine ends up in the bloodstream carrying amino groups. It's apparently mostly from muscle cells. Yeah, here's the slide they label alanine from muscle cells. And here's the figure from the book that shows glucose being oxidized to make pyruvate, but also proteins being oxidized to make amino acids. Glutamate is formed, but again, rather than secreting the glutamate, alpha-ketoglutarate is regenerated, and alanine is made, alanine is secreted. And then in the liver cell, the alanine, the amino group is taken back from the alanine, given back to alpha-ketoglutarate to make glutamate. Pyruvate is generated, maybe the liver makes some glucose. But the important thing is, again, that the alanine is carried the amino group to the liver cell. So in the liver cell, the alanine is, the amino group is going to be given back to glutamate, right? And so, again, from the standpoint of the liver, the amino group is collected in the liver, and now here's the glutamine again, finally we talked about a few minutes ago. So here's the amino groups. All right, so these three molecules are coming into the liver. And so the liver needs to be able to make ammonium ions so it can make urea, and it needs to be able to make aspartate so it can get the other nitrogen for the urea synthesis. So liver, we're getting glutamate from the blood, we're getting alanine from the blood, but this is reacting with alpha-ketoglutarate to make glutamate and pyruvate. All right, so that gives us glutamate. And we're getting glutamine. Glutamine is undergoing hydrolysis catalyzed by the enzyme glutaminase. So the amide side chain can undergo hydrolysis to release an ammonium ion. So water is acting as a nucleophile, ammonium ion, NH4 plus is the product, and this is catalyzed by the enzyme glutaminase. And that's shown here by taking one of the amino groups off the glutamine, and there's releasing ammonia. And so, no matter how these things get to the liver cell, they're going to be used to make glutamate. And again, there's one ammonium ion. So the issue is now how to get the amino groups from glutamate. As shown on the slide, there's an enzyme that's going to release ammonium ion from glutamate. There's also an enzyme that's going to make aspartate. This is an aminotransferase enzyme, aspartate aminotransferase. Right, so that's going to give us the ammonia that we need to make urea coming from glutamate. Aspartate also coming from glutamate. And then the urea cycle, which begins here, is going to take all this stuff and put them all together. So I'm going to go through these reactions next time. I don't know how many more reactions I'll do. I might have some quicker questions about protein-dependent enzymes, because there's a lot of really fun reactions. And then we're almost done with the semester. So if you have any questions, so we'll see you on